On behalf of the Science Library, it's a pleasure for me to welcome you all to this year's Rosseland lecture. And I will now hand the microphone over to the leader of the Institute of Theoretical Astrophysics, Per Lilje.
Thank you. On behalf of the Institute of Theoretical Astrophysics, I want to welcome you all to this year's Rosseland lecture. Svein Rosseland, he was really the founder of astrophysics in Norway. He became the professor of astronomy in Norway in 1928. He was born in 1894, and he managed also to get money to build our department building in 1934, and did quite a lot in astrophysics in the 1920s, 30s, and really building up astronomy as a field, as a large field in Norway, and our institute to become a major place. So we are celebrating Svein Rosseland's legacy by holding these annual Rosseland lectures, which are the greatest events of our institute. We started with this in 1994 at the 100th anniversary of the birth of Svein Rosseland. So each year we invite one world-leading expert on some field in astrophysics to give a lecture. And this year our Rosseland lecturer is Hiranya Peiris. She was an undergraduate student in Cambridge, then she went to Princeton in the US, did her PhD there. Then she was a Hubble Fellow at the University of Chicago at the Kavli Institute there. Then she came over to Cambridge again, where she also was at the Kavli Institute of Cosmology. In 2009, she got a faculty position at University College London. In 2015, she became a full professor at UCL. And from last year, she's also, in addition to being professor at UCL, she's also a professor of the University of Stockholm and director of the Oscar Klein Center for Cosmoparticle Physics. It's a bit interesting. This brings me to Svein Rosseland again, because when they both were research fellows, Svein Rosseland and Oscar Klein, with Niels Bohr in Copenhagen, in the beginning of the Institute of Theoretical Physics, which now is the Niels Bohr Institute, they were first in a big room in the mathematics department before that building had been built. And this big room had Niels Bohr sitting on his desk in the center, and in one corner was Svein Rosseland sitting, and the other Oscar Klein was sitting. So, and in fact, Svein Rosseland's first ever paper was a paper with Oscar Klein. So it fits very well. Hiranya has also done remarkably in teaching and in outreach, and we'll now hear her in outreach and talking about the universe detective story.
Thank you very much. Can you hear me in the back there? Okay, is it possible to get the lights slightly down? Got a lot of movies? No?
It's for the streaming.
Oh, I see. Okay. Okay, so that's fine. I'm very, very happy to be here giving this lecture, and I'm glad to see all of you here. It's a lovely day outside, but you're in here wanting to hear about science, which is a great thing. And I want to start with a little bit of history. So this is the Flammarion woodcut. It shows a person trying to pierce through the dome of heaven and trying to work out what makes it all work, what makes it all tick. So cosmology is one of the oldest branches of science. It's part of astronomy, but for a very long time, cosmology was a very speculative field. We had very little data. So it was a fun playground for theorists, that you could just build models of the universe and speculate about the relative worth of theoretical models. But this has changed completely in the last 20 or 30 years, and it has been done because of a flood of data. A huge amount of observations about the universe. That has allowed us to try to unravel and piece together the history of the universe and even its origin and its fate. I'm going to tell you a bit of this detective story, how we have tried to work out the evolution of the universe, and where we are now. And it should hopefully become clear that the more we have learned, the more we have understood how much more there is for us to understand, and how much we don't actually know. So let me start with a very simple fact about the universe, which is the thing that makes us able to do all of this. This is the fact that the light has a finite speed. Okay? So when you see light from distant sources, like even the nearest stars, it left those stars a very long time ago, and by the time that it reaches Earth, you are seeing those stars as they were in the past. So we can repeat this exercise to more and more distant parts of the universe, and when we get light from more and more distant parts of the universe, we can use that light as a time machine to look back into the past and see what the universe was like when it was younger. And repeating this exercise to the earliest light you can see, you come to something called the cosmic microwave background. I'm going to call this the CMB, because cosmic microwave background is a little bit of a mouthful. So the CMB is the very earliest light you can see in the universe, and it is essentially the leftover heat of the Big Bang. So let's start with the story of the dawn's ancient light. And we can start at home. We live inside a galaxy. And we are looking into the universe through the stars of that galaxy. And many of these maps I'm going to show you shortly come from taking data from all over the sky and projecting it onto this sort of elliptical projection. And in the middle here, you can see the galaxy. That's a visible light. That's near infrared, far infrared, sub-millimeter, all the way to the microwave. Then you turn up the contrast by a factor of 100,000, and you start to see the cosmic microwave background. So along this axis here, that's still emission from within our galaxy, microwave emission from our galaxy. And above and below the galactic plane, you see these patches of green and blue mottles, and these are essentially tracking density variations very early on in the universe, when it was only about 380,000 years old. So the universe now is about 13.7 billion years old. The reason we have been able to figure that out is by studying this light, and I will tell you about that later. So the very early universe essentially then had slight variations in density. So this is 1 part in 100,000. And those variations correspond to essentially over-densities and under-densities compared to the average density of the universe. So if you got a little bit more matter in some part of the universe compared to another part, what happens? There's gravity. Gravity makes things attract, and so matter falls into gravitational potential wells, and that makes structure form. So these stuff that you're seeing up and down, above and below the galactic plane, that corresponds to the origin of cosmic structure. Everything in the universe today formed out of these little variations in that early light. So the cosmic microwave background was discovered by accident, essentially, in 1964 by Penzias and Wilson. They were operating an experimental radio telescope in Bell Labs in Princeton. And they built this not to study the Big Bang, but to study the gas between stars. And they started operating this, and they found this noisy hiss coming from all over the sky. They didn't know what this was. They tried to figure out whether there was a problem with the instruments. You probably heard about the famous story where they thought it was a white dielectric substance, pigeon droppings, inside the telescope. They went into the telescope, scooped out the pigeon droppings. There was still a noisy hiss. And so pigeons, unfortunately, if you remove them from the site, they like to come back home. So I recently learned that the pigeons were actually shot. That is very sad because they gave their lives in vain. So it turned out that they went over to their colleagues at Princeton and found out that they had scooped them, essentially. They were trying to find this light from the Big Bang, and that had been accidentally found by Penzias and Wilson. So they got a Nobel Prize for their trouble. And then I'm going to fast forward to 1992. This is the Cosmic Background Explorer satellite, so it's a NASA satellite, and it took the temperature of this very early light. It's very cold. It's about 3 degrees above absolute zero. And it did something far more fundamental and paradigm-shifting than that. It actually discovered that this light was not uniform across the sky, but it had these little ripples, the primordial ripples from which everything that we see today in the universe has come from. And so that is the seeds of structure formation, and that was, again, a profound discovery that earned the people that were part of the COBE team the Nobel Prize. Now I'm going to try to bring together the fact that, okay, there are all these amazing discoveries, and it seems like science moves from discovery to discovery to discovery. I want to try to bring across in this talk something about the people behind these discoveries, and the fact that it's not proceeding as this clockwork march towards progress, but there are little side steps, and there are teams of people that are working very hard behind these discoveries. So here are some of my colleagues in some interesting costumes. There might be people in the audience that don't know what that is. That is a computer, okay? So something that's going to come through my talk is the importance of computers and computational methods that are a critical ingredient, a critical part of the cosmological detective's toolkit. And so now, fast-forwarding another 10 years or so, I come to the Wilkinson microwave anisotropy probe. That's again a mouthful to say, try to say that quickly a few times. And so this is a evolution in experimental capability. It's a much finer resolution experiment and much more sensitive detectors. And when you have that, you can take the same map, so remember this is a projection of the full sky, and take a better picture of it. And when you take a better picture of it, details come into view, just like you might be short-sighted and you put on a pair of glasses or contact lenses, you can see better, there's more information. And that information allows you to work out something about the physics of the universe. So you can see now the team has grown. This is still a tiny part of the WMAP team. This is essentially the science team. This is a picture that I'm very fond of because I'm actually there. I did my PhD on this experiment. And we are all looking very happy that day because it was 6 months of sky close. That means we got a full scan of the sky. And we had just plotted the data and compared it to a model for the first time. And that was a very good day. This is David Wilkinson. So the satellite is actually named after him. He was a pioneer of cosmic microwave background observations and experimentation. And sadly, shortly after that meeting, he passed away, and the satellite was renamed after him. But he got to see the data, and he was very, very happy that day. So what is this cosmic microwave background? So the very early universe was very hot. Everything was in a hot, dense state. There were no neutral atoms. Atoms were dissociated into their nuclei and their electrons. And there was a sea of electrons pervading everything. And particles of light, or photons, could not get very far because every time they tried to move, they would scatter off an electron. So that means that the universe was opaque to light. It's just like if you look at okay, it's a sunny day today, but imagine that there were clouds, right? So you know that there's sun behind the clouds, but you can't see the sun. You can only see up to the surface of the clouds because beyond that, the light from the sun is being scattered within the clouds and the particles in the clouds. Something similar is happening here. So this light is being scattered by electrons. And eventually, as the universe expands, something it does to light is that it stretches out their wavelengths. And the universe cools as it expands. eventually wasn't hot enough to keep this gas ionized anymore, and neutral atoms formed. And at that time, and it's a very sharp transition compared to the span of cosmic time, basically the universe became transparent to light. And the cosmic microwave background is also called the last scattering surface, because that's the last time, essentially, that these photons scattered. And since then, they've been coming to us from that very early time through the span of 13 billion years of cosmic history. And these photons have had very lonely journeys. They have very rarely scattered or interacted with anything before they were eaten by our detectors. So that means they carry pristine messages from the time that the universe was very young, and they show us a baby picture of the universe. And when we look at this baby picture, what we see is a cosmic tug of war. It is a battle between gravity and pressure. So this gas of electrons and photons, it has a pressure. Pressure tends to push things out. Gravity tends to make things collapse. So in this sea of electrons and photons, you are setting up sound waves. So when we look at this gas in the early universe, and when we look at the cosmic microwave background, you are seeing sound waves imprinted in this gas at the time that the universe became transparent. So when you think about sound waves, you can take this data and actually you can turn it into a sound signal, and you can actually hear what this sounds like. And it sounds like this. So that's enough of that. It's not a noisy hiss, right? It's not something that's white noise. You can hear a scale in it. And just like that, there is a scale in the cosmic microwave background. There's a typical size of the spots in the cosmic microwave background. And we know how to calculate the size of that typical angular scale in the early universe. It is a standard ruler. And then you see how it's projected onto the sky, and then you can work out how far away that surface is. Or analogously, because the speed of light is finite and we know what it is, you can work out how old the universe is. So how do you actually do that? So, okay, we can't make universes in the lab, which is a good thing, but we can make universes in a computer. So this map is a fingerprint of a model of the universe, a cosmological model. And these models can have very different physics in them, and they have very different parameters, and you can simulate many different types of these maps. And each one can be compared to the one that we actually do see. So that means that you can actually throw out the models or the bits of physics that don't work, and keep the ones that do work. And by this process of winnowing it down, you can actually work out which cosmological model actually fits the data. And it's a remarkable fact that this entire map and all of the little pixels in it, all of this data, can be described by a cosmological model with just 6 parameters. It tells you something about the constituents of the universe, how much baryonic matter, a matter described by the standard model of particle physics, how much dark matter, how much dark energy, what was the level of fluctuations in the early universe, when did the first stars form, and what is the geometry of the universe. So those ingredients allow you to construct a cosmological model that fits all of this data. So that's great, because there's a very good fit between this model and this data. But I just said a whole bunch of things which are actually a big extrapolation of physics. What is dark matter? What is dark energy? Where did these fluctuations in the very early universe come from? All of those bits of observed data actually correspond to huge extrapolations of what we can test in the lab, for example, at the Large Hadron Collider. So let's put that story back together, though, to show the history of the universe. So when you go into one of these cold spots, that's an overdensity, so it attracts matter, and that matter will continue evolving in this dark universe, no stars yet, and eventually the first stars will turn on. And they flood the universe with ultraviolet light, and then matter and gas stream along these scaffolding of dark matter filaments and form galaxies. So now the universe is starting to look more and more like the modern universe. And when we observe the cosmic microwave background, you're looking back through all of this turbulent history at a very pristine early light. So that's the story of the history of the universe that we have been able to figure out by studying data from WMAP. And now I'm going to fast forward another 10 years to Planck. So Planck is a third-generation CMB satellite, and this satellite is the first European satellite to study the cosmic microwave background. And it's a huge leap forward from the previous satellite in terms of sensitivity and resolution. So again, the picture of the universe sharpened once again, and that allows us to gather yet more information about our cosmological model. And the size of the teams has grown yet again. So this is just part of the Planck team. And I think that was, again, one of the first meetings at which we had serious cosmological results, and it's a very good day. This is just one part of one of the two Planck teams. There's tremendous involvement at Oslo in this experiment, and a lot of really fundamental work that was done here as well. So Planck, here is an animation of it. It's operated well outside the orbit of the moon, very far away in the cold of space. But it had to measure temperature variations across the sky of a millionth of a degree. That means that its detectors had to be cooled to 0.1 degrees above absolute zero, so very, very cold, so that their own internal heat did not swamp this pristine signal from the sky. And from that point, it scanned the sky several times and produced maps like that. And these maps, when you disentangle them from the emission from the galaxy, allow us to test the cosmological model at ever greater levels of precision and accuracy. So if you then go back to the very first version of that, that's COBE, that's WMAP, and now we come to Planck. You should be able to see the same large-scale structure persists in these maps, but you're starting to see finer and finer detail. One of the consequences of that level of increase in precision means that we can make statements like this. This is an astonishing statement. The age of the universe is 13.82 plus or minus 0.05 billion years. So, you know, this is a question that humanity has been trying to answer for a very long time. And now we've got percent precision on that number. So it's saying something very fundamental about the history of our universe, that we can actually answer questions like this with great precision. And this data is so precise that it allows you to actually do something even more audacious and rewind time back past the last scattering surface, so that's 380,000 years after the Big Bang, almost to the Big Bang itself. In fact, we think we can go back, so that's a decimal point followed by 32 zeros and a 1, 10 to the minus 32 seconds after the Big Bang. And at that time, all of the structure in the universe is thought to have originated from quantum fluctuations in a field, a scalar field, called the inflaton. So what is a scalar field? So you probably have heard of the Higgs particle, which got a Nobel Prize a short time ago. It was produced for the first time at the Large Hadron Collider. So it's good that they found that, because in cosmology we have postulated scalar fields to exist in the early universe for quite some time. But that was a huge extrapolation of laboratory physics. So the Higgs is the first laboratory-produced verification of the existence of fundamental scalar fields in nature. So I have to say that it's, okay, so the Large Hadron Collider is producing particles at energies that are 1 trillion times less than what would have occurred in the very early universe. So it's still a big extrapolation of physics. And during this time, like in a tiny, tiny fraction of a second, the universe is thought to have expanded by a factor of 10 to the power 30. Very quickly, in a sense, the universe expanded faster than the speed of light. And these tiny little quantum fluctuations got stretched out by the expansion of space, and they actually source all of the structure in the universe. So in a sense, everything around us, everyone in this room, ultimately came from quantum fluctuations in the early universe. So that's the story. So this era of the origin of structure is called inflation. This is not what the economy does, it is something the universe does. Okay, so how can we test this idea that sounds like science fiction? So this theory has the virtue of making some precise predictions for what the patches of hot and cold spots on the cosmic microwave background should look like. In particular, it tells you the relative power in the fluctuations as a function of scale. So that probably sounded not very understandable to some of you, but it is actually, okay, let's try this analogy. So when you listen to a piece of music, some pieces of music are treble heavy, some pieces of music are bass heavy. There's a frequency balance, right, in pieces of music. So the bass corresponds to sound waves which have long wavelengths. The treble corresponds to sound waves that have short wavelengths. Okay, so it's the same concept that we're talking about in music as happens in the early universe. So let's make this analogy that small scales are treble and large scales are bass. Okay? So if the universe was treble heavy, that it has more power in the frequencies at small scales than in large scales, it could sound like this. And if instead it had more power in the large scales compared to small scales, it would be bass heavy, and it could sound like this. If it instead was balanced, a balanced universe that had roughly similar power in the treble and in the bass, it could sound like this. Thank you, Mr. Bach. So actually, inflation predicts that the universe is roughly balanced. And when we go and measure these fluctuations as a function of their frequency and how that relates to scale, we find that that is a prediction that is confirmed by the data. So inflation isn't the only model or the only theory for the origin of structure. There are many other theories. Some are less big extrapolations of laboratory physics. For example, there are cosmic strings or textures. These are phase transitions in the early universe that could have produced the fluctuations. So all of these different theories make predictions for what the cosmic microwave background should look like. And it doesn't look like these, and it looks like that one. So that's one example of the way that without actually doing a laboratory experiment, we can say that these kinds of physics are probably not what originated structure in the universe. It's probably something much more extreme, like that one. So that is another bit of unknown what is the origin of structure that Planck has shed some light on. And now I want to turn to the dark side of the universe. So as these particles of light, these photons, travel through the universe, they're very slightly deflected by large structures made out of dark matter, like clusters of galaxies. Very, very tiny deflections. So that actually changes the appearance of the map that we actually see. So these deflections are the effect of gravitational lensing. So you can actually hopefully see a very tiny difference between the unlensed version of this map and the lensed version. So by inverting that effect, if we could do that, you can work out how much dark matter there is along each line of sight in each pixel. And of course, we only see the lensed version of the map. We don't see the unlensed version. But we know exactly from Einstein's theory of gravity how this effect of lensing should affect the map. We know how it would affect the statistics of the map. And so we can actually construct a map of the dark matter integrated along each line of sight. So when you do that with the Planck data, you see an image like this. Most of what you're seeing here is actually noise, just by eye. There's a statistical signal in there, and it's very strong. It's about 30, 40 sigma. But at this level of the map, this is more like the COBE map of the cosmic microwave background from 1992. It's the birth of a new way of looking at the universe, and we are right there at the start. So the next generation of experiments will improve this map in the way that the primary fluctuations of the cosmic microwave background has been improved through different experiments through the subsequent decades after COBE. So this is a new window of the universe, and this is not the only way we can map dark matter, but it is a very powerful way. So given the cosmic microwave background and other data, this is essentially a pie chart showing what is the energy budget of the universe. And visible matter, which is stars and gas mostly, is only about 5% of the energy budget of the universe. Think about what that means. Everything that we've ever been able to test in the lab, the standard model of particle physics, it's in there. 27% of the universe is dark matter. And dark matter is inferred from a very large set of different astronomical observations, including the cosmic microwave background, but it has not been detected yet in the laboratory. There are, I suppose, relatively simple extensions to the standard model of particle physics that could tell you what dark matter is, and many different experiments are looking to detect those in the lab. However, dark energy, I think it's fair to say, is a label given to an effect we don't understand. That represents a much, much greater shift in the paradigms of physics than dark matter. We actually don't understand what dark energy is. It could be tied to the vacuum energy of the universe. It could be something even more exotic. It could be the modification of Einstein's theory of gravity. All of those things are essentially saying, here be dragons on a map. We don't actually know the answer to that question. And there's a huge amount of effort trying to understand what is dark energy, both from the theoretical side and from the observational side. And from the observational side, this leads you to big surveys of galaxies. That's where I'm going to go next. So the sun emits at visible wavelengths. So do most stars. So the optical wavelength, the visible wavelengths of light, are a good way to study the universe. So we've looked at the microwave now, and now we can turn to the optical. And so if you start to map out the universe in visible light, you see galaxies, because galaxies are made of stars. And we've been mapping the universe in this way since the 1990s. This is not a simulation. This is about 400,000 galaxies mapped by the Sloan Digital Sky Survey. Each one of these pictures is an actual galaxy in the sky, and you can make a fly-through of it because we can work out how the galaxies are related to each other. And the first thing that you see is that they're not uniformly distributed. They cluster, they swarm like fireflies in the night. And that clustering tells you something about how structure forms, and it tells you something about how dark matter is distributed, how dark matter and dark energy are evolving in their balance as the universe ages. And when you're seeing these galaxies, it is like seeing a marker for there's stuff here, there's less stuff over here, there doesn't seem to be that much more stuff over there. And it's like looking at, say, an image of the Earth at night. Okay? So these days, if you went in a satellite and you took an image of the Earth at night, you would see where there are people, right? You would see cities. You would be able to work out with quite high level of confidence where there are more people and where there are less people. In the same way, galaxies represent a biased marker of where there is dark matter. And they are like the tips of the iceberg, and beneath there is this scaffolding, and it's made of dark matter. And you can trace that dark matter by studying where there are galaxies. And again, like in the case of the cosmic microwave background, just making these observations doesn't really teach us about the universe. To do that, you have to have a theoretical model for how to interpret this data. And the level of complexity of now producing predictions for how to model a galaxy survey is far more difficult than it is to predict the cosmic microwave background. This represents very nonlinear physics. And to do that, you need supercomputers. So here is a simulation of a cluster of galaxies and a big filament forming inside a supercomputer. So when you have these kinds of simulations, something like this would take months to run on, say, 100,000 cores. It's a very, very big effort that you have to make in order to get at the theoretical underpinning of what you would then observe in galaxy surveys. So I showed you how the size of cosmic microwave background collaborations have changed over time. You need more people to do all of this very intricate work of piecing together the different parts of the puzzle, the theoretical parts, the data analysis part, the statistics part, actually to clean the data enough that you can make any sense of it whatsoever. So I'm not going to even now show you pictures of people. I'm going to show you where they're from. So this is the Dark Energy Survey, which is an experiment I work on. It's a large survey of galaxies that is made from a telescope called the Blanco telescope in Chile. And it is going to map about 300 million galaxies. And the people that have worked on that experiment come from all over the planet. Science is a very international enterprise. These days, we hear a lot of talk about borders, and we don't want those kinds of people, and we want these kinds of people. Science doesn't work like that. So science works in a way that everybody comes together from all over the world, and they try to answer the fundamental questions about the universe, which is a much, much better way to live, in my opinion. So I actually come from this place, that's Sri Lanka, over there. But you can see what an international enterprise it is. This, I don't know if you can see that from the back, but all of this image, this is the Blanco telescope, where the Dark Energy Survey is carried out from. Can you see it's made of little pictures of people? These are all the women in the Dark Energy Survey. So this is a wonderful representation of, there is this, okay, you watch all of these popular science documentaries on TV, it's some guy going on about blah, 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 and it sounds like all of that information has just arrived in their head, right? No, it's a very human enterprise. It's, working daily with your friends and colleagues from around the world. It's a very social enterprise. The survey that I'm most excited about right now and spending a lot of my time on is the Large Synoptic Survey Telescope. So it seems like we astronomers need to work on the names we give things. That's also a mouthful. Let's call it LSST. It's a survey of about half the sky, of the southern sky again. It turns out that there are lots of high, cold mountains in the southern hemisphere, and it's a good place to build telescopes. So again, this one's going to be in Chile. So the dark energy survey, 300 million galaxies. This is a completely different way of doing survey astronomy. So this is going to be a survey of the sky for 10 years, where you return to the same point on the sky with your camera, basically every 3 days or so. So it's a movie of the sky. It's going to show us the universe in a way that we haven't ever looked at before, except on little patches. It's going to show us how the universe evolves. So, of course, there are galaxies that are basically static, and they stay there for the entire 10 years, but there'll be explosions like supernovae. We might be able to work out what are the sources, the optical counterparts of the gravitational wave sources that have recently been detected, for example. So that's going to be 37 billion objects in space and time. It's going to be 30 trillion measurements. This is big data. It's big not just in terms of its volume and its data rates, but in terms of its complexity. And astronomers can't, by themselves, actually make sense of this data in order to understand more about the universe. So this experiment has not just astronomers working on it, it has particle physicists who are used to massive volumes of data that they analyze in the LHC, for example. It has computer scientists, it has statisticians, people from Google are involved. There are lots and lots of people coming together from different fields now, it's very interdisciplinary, to try to understand from this data. You know, of course, we are still very interested in these unknown questions about the universe, the dark matter, dark energy. We want to make an inventory of the solar system. So you see moving objects, including asteroids and near-Earth objects. If there's one coming to hit the Earth, we should hopefully know about it through this experiment. We can make a movie of the universe and work out where there are massive explosions going off in the universe. And we can map the Milky Way, our own galaxy, our own home. And by mapping the Milky Way, actually, it has a connection to dark matter as well, because the evolution history of the universe, of the Milky Way galaxy, is actually captured in terms of what dark matter models will tell us about structure formation at very small scales. I actually get goosebumps when I look at this. This data is coming very soon. The first light of this experiment is going to be in 2019, which is not that far away, and it is being constructed right now in Chile on a mountaintop. This is, again, coming back to the idea of people. This was an image taken at our last collaboration meeting in February. And again, it shows astronomers, cosmologists, computer scientists, statisticians, particle physicists, engineers, all of these people coming together to make sense of this experiment when it starts to deliver this firehouse of data in a couple of years' time. So we've briefly touched on the fact that observing the universe at different wavelengths, essentially. I showed you the microwave, I showed you the visible. You get a different view of the universe. And the moment that you see the universe from different sides, you can work out more about what makes it tick. So it's not just those two wavelengths that we are observing the universe at. So here, starting from very high energy, short wavelengths, we have gamma rays, X-rays, optical, I showed you, galaxy surveys. This is emission from gas. This is far infrared. This is the microwave, that's the image from Planck. And when you go even longer wavelengths to the radio, you start to hit on another big data project, which is the square kilometer array, which is going to happen both in South Africa and in Australia, a huge project to cover a square kilometer with radio receivers and map the radio sky. Again, a very big project. So this is mapping the universe in light at all wavelengths. Now we've started to map the universe in a completely different way as well. This is the gravitational waves from LIGO. So this is like going from just looking at the universe with your eyes to rather feeling its vibrations, the vibrations of space. It's a completely different new window on the universe. And what we're starting to map out are, again, a different way of looking at the universe. And that relates to the periods of the gravitational waves as well. So LIGO detects millisecond period gravitational waves. A big experiment in space called LISA could measure gravitational waves at periods of minutes to hours by using pulsars, these searchlights, very rapidly spinning compact stars in the universe. They exist already in the universe. We're not going to put them there around the universe, but by measuring their periods very, very precisely and using them as an array that nature made for us, you can work out gravitational waves from periods from years to decades. And coming back all the way to the cosmic microwave background, by measuring the polarization of the cosmic microwave background, you can measure gravitational waves of periods of billions of years. And that again tells you something very fundamental about the early universe. So this theory of inflation I told you about briefly tells you that not only do quantum fluctuations produce all the density fluctuations in the early universe, but it should have set the universe ringing like a bell. And that produces gravitational waves, these gravitational waves of periods of billions of years. And those translate into polarization in this map of the cosmic microwave background. It gives light a certain handedness. That polarization signal is very, very weak. So in these kind of textures on top of this map, you can capture some kind of visualization of what this polarization could look like. And by measuring these data at a much, much greater degree of sensitivity, you could try to capture this elusive signal, this smoking gun of inflation. I'm going to end with something that's going to be much more speculative than what I've told you so far, which is that there's quite good evidence now for this theory of inflation. And if you take it seriously, it actually predicts that the universe is much, much bigger than the part of it that we can see. And that there might even be other universes out there. This is this idea of eternal inflation. It says that inflation doesn't stop everywhere in the universe, it only stops locally. And where it has stopped locally, that would be a bubble universe. And our universe, the observable universe, would only be a tiny part of that bubble, but there's loads of other bubbles out there. And this, again, sounds like science fiction, and there's quite a high possibility that there is, but that is what this theory implies if you take it seriously. So, ever since we started thinking about our place as human beings in relation to the universe has been getting to be a bigger and bigger and bigger place. We learned that we lived on a planet, which is not the center of the universe. It orbits a sun. Our sun is an insignificant star in a galaxy. It's only within about 100 years or so that we even knew that there were other galaxies. Now we are mapping the size of the observable universe all the way to the end of it, which is the cosmic microwave background. And this theory tells you that our universe might be an insignificant speck in the sea of universes as well. This might seem like a very scary thought to some people, but I actually find it amazing that in such a, we could be very insignificant, but we have somehow managed to work out all of this by studying the universe, using our brains, and working together. I'm going to end there. Thank you very much.
Thank you for this amazing journey through space and time. I assume you are able to answer some questions here. So,
Very pleased.
is there any?
Yes.
Yeah.
Thank you very much. It's very nice that you make this so friendly. You know that many here, like myself, I'm not an astrophysicist or a cosmologist, and I could benefit a lot of this.
Mm-hmm.
And so in the beginning of the presentation, you said that there seemed to be a spatial length scale for the universe, right? So like a natural ruler or something
Yep,
like that.
that's right.
But then when you mention that the universe is not bass heavy or treble heavy, there is somehow balanced. This is in accordance with inflation theory, right? Does that mean that there is no temporal length scale? Could I say that there is a ruler for space, but no ruler for time in the universe?
So that's a very good question. It's a very deep one. So I'm trying to work out a way to answer it that doesn't get technical. The ruler that I talked about is essentially the fact that these fluctuations mostly happen on spots of about the size of a degree. Okay, so that ruler size is not necessarily impacted by the balance of frequencies between the treble and the bass. It's a more fundamental, easier to measure quantity. And from that, you can work out the basics of the cosmological model. And on top of that, by measuring this balance between treble and bass at different scales, not just at that 1 degree scale, you can work out something about the initial fluctuations in the universe and test inflation. The temporal scale, it's an interesting one. I think that the fact that there is a arrow of time itself is a deep puzzle. It's probably as deep a puzzle as dark energy. Why is our universe evolving in one direction in time? So the cosmic microwave background doesn't necessarily tell you something about why there are different balance of constituents in the universe as well. So at the moment, the universe has very little radiation in its energy budget, about 5% of baryons, and then dark matter, and most of it is dark energy, right? That wasn't always the case. And that's because these components actually evolve at different rates. So their balance of power essentially changes. So the very early universe is full of radiation, and now it's like an insignificant part, less than 1%. So that gives you essentially the ability to change the look of the universe as it evolves in time. So if there hadn't been a part of the universe, history of the universe that was not matter dominated, you would not get galaxies because they wouldn't actually have time to cluster because radiation tends to push things out. So the relative balance of these components gives a kind of richness to the evolution history of the universe. But why this balance has been set in this particular way, we don't know the answer to that question either. So fundamentally, we don't know why there's an arrow of time. And less fundamentally, but even more unknown, is that, why are these components fixed in this way? It could be completely random. If there are lots and lots of other universes, they might have very different levels of balance between these components. So that's a very long-winded answer, but your question is a very fundamental and interesting one. Thanks.
More questions?
Yes, this one there.
Hi, thank you very much. I had a question. Why is inflation 10 to the 30 and not 10 to the 40 or 10 to the 50?
The factor by which the universe expanded. Okay, that's again a very insightful question. That is actually a lower limit that's set by how much expansion in this initial phase you need to explain the fact that the universe is as homogeneous as it is in the very early times. Now it's not homogeneous, right? There are lots of galaxies and lots of empty space. But the early universe, as I showed you in that map, the variations are 1 part in 100,000. That tells you that if there were any initial very big inhomogeneities, they have to have been erased. And what inflation does is to erase pre-existing structure. Like you would never expect the universe to be perfectly smooth with tiny little fluctuations. You would expect a case where it's exactly smooth or with big fluctuations, right? So it's got a very high degree of smoothness with tiny fluctuations. That tells you that the initial structure has to have been erased, and you need at least 10 to the 30 factor of expansion to arrange that. So it's an observational constraint, actually, on inflation. But inflation could persist for a much, much longer time than that. And in fact, this theory of eternal inflation tells you that it never stops in certain parts of space, only in some parts. So you can say that that's an observational bound, that's a minimum. Yeah.
Anybody else? Well, if no more questions, I think you stunned everybody here. I want to thank you for your presentation here. Here's a little gift from
Thank you.
the Institute. And I also want to thank the Science Library for hosting this event. So thank you all.
Thank you.
Just for those who are from the Institute or guests who are going to our dinner, the bus will be outside in that direction in the street, leaving at 5 o'clock. So we still have 50 minutes either to stay here or to go somewhere else in the meantime.